chapter 14. Chapter 14, we did, Charles' law, the other laws, the combined gas law. We're going to look at a couple more laws. The law of combining volume, or Avogadro's law. Gases at the same temperature and pressure, the amount of gas depends on the volume. So, if you buy a tank of gas, that tank of gas could be empty or could be full, gas. It depends on the pressure and the temperature. And so a helium tank could be totally empty because it has zero pressure, zero gauge pressure in there. But if we have gases that are at the same temperature and pressure, then we can figure out, like a 10-gallon helium tank would have twice as much helium as a 5-gallon helium tank, as long as both are at the same temperature and pressure. If both aren't at the same temperature and pressure, then we can't say anything much. The 10-gallon could be empty. This is called Avogadro's law. In other words, the volume of the gas is directly proportional to the number of moles, or the amount of the gas here. And so what we're going to do is we're going to keep the pressure and the temperature the same for all of these. And we're just going to look at the volume. And so if I have 50 milliliters of O2, 100 milliliters of H2 would be twice as much gas, that is twice as many molecules. So in this particular example, let's say 50 milliliters of O2 has this many molecules, 4. That means 100 milliliters of H2 would have double that, 8. Let's see here. And then we end up forming 100 milliliters of H2O, which would have the same number of molecules, although this should be 8 as well. 1, 2, 3, 4, 5, 6, 7, 8. And so we can figure out how many molecules the gas has based on its volume. And so if we have a reaction like this is the reaction of hydrogen and oxygen, we can come up with simple ratios for the reaction. And so when we look at a balanced chemical equation like this, 2 hydrogens gas plus an oxygen gas yields 2 H2O. And in this case, we're going to make this a gas. Normally it's a liquid, but in this particular example, it would be a gas. And so this is 2 moles. 2 moles or molecules. This would be 1 mole or molecule. This would be 2 moles. And so this is the mole ratio. Now the thing is, if T and P are the same, that is, if we say T and P are constant, it doesn't change, then this is also the volume ratio. And so rather than moles, we could say, for example, liters or gallons. And so it would be volume ratio. This is Avogadro's law. And so this could be 2 gallons of hydrogen gas. We need 1 gallon of oxygen gas, and we'd form 2 gallons of H2O liquid. But we don't work with gallons that much. We mainly work with liters. So we could say this: I'd need 2 liters of hydrogen for every 1 liter of oxygen to form 2 liters of H2O gas. And so we have the volume ratio. Because if you have twice as many molecules, it's going to take up twice as much space, as long as you're not compressing it or expanding it. So here's another illustration of Avogadro's law. Here I have 3 particles. If I double it to 6 particles, I'm going to have to double the volume. Otherwise, if I double it and I keep the volume the same, the pressure's got to jump up. But we maintain constant pressure. The way we maintain constant pressure is this is a movable lid. And so on one side we have the weight of the atmosphere. On the inside we have the weight of the gas. So they balance each other out. triple it from the original, then I'm going to triple the volume. So here, double the amount of gas, triple the amount of gas. Double the volume, triple the volume. So we can do some simple stoichiometry with gases. The simple stoichiometry we can do with gases is, for example, if I have 5 liters of oxygen, how many liters of hydrogen will I need to react with it? Okay, 10 liters. I need twice as much hydrogen. If I have 5 liters of oxygen that completely react, how many liters of H2O gas will I generate? Well, it's twice as much, so 10. Now, it doesn't really matter what the particles are. You know, the particles are going to take up a certain amount of space. So, you know, we think oxygen molecule versus a hydrogen molecule, they're different sizes. Yes, they're different sizes, but it's not going to impact. So this could be oxygen, this could be hydrogen, this could be H2O gas. They're all going to take the same amount of space. That's a weird thing about gases. Take the same. The particles themselves are negligible, you know, and so when we look at the volume of the gas takes into consideration all this empty space plus the particles. When we look at a gas, it's mostly empty space. The particles themselves take up very little of that space. And so even if we're talking the difference between an oxygen and a hydrogen, hydrogen is a much smaller molecule, they're both really small. So they both don't have any impact. It's the collisions that are going to cause this. Collisions of the temperature. Collisions would be related to pressure. And so we have the ideal gas law. And the ideal gas law is going to be a combination of Charles' law, which is volume and temperature, Boyle's law, which is volume and pressure, and Avogadro's law. We combine those 3 gas laws and come up with a new gas law called the ideal gas law. And, why do they call it an ideal gas law or ideal gas? Because not all gases behave the same. You know, some behave more ideally than others. So ideal gas is a hypothetical gas behaving as an ideal over all temperatures and pressures. For example, hydrogen is much more ideal gas than steam here. You know, hydrogen stays as a gas to very low temperatures and high pressures. Whereas steam doesn't stay a gas. You know what's going to happen to steam? It's going to condense at 100 degrees C. And so steam is what we call not a very ideal gas. You know? It stays a gas, yeah, but the temperatures have to be very high. The pressures have to be low. Otherwise steam won't stay a gas. And so there are some gases that are more ideal than others. So the most ideal gas on the periodic table is helium. Helium stays a gas, but it's not perfectly ideal. You know, perfectly ideal gas should stay a gas until 0 Kelvin. But what happens with helium is, helium, you cool it down, you cool it down, you cool it down, stays a gas until you hit 4 Kelvin. At 4 Kelvin, do you know what happens to helium? It liquefies, and so it's no longer a gas. And so helium's a gas from 4 Kelvin on up at normal pressure. You know, water's a gas at 373 Kelvin and up under normal pressure. You know, and as the pressure changes, things can become more ideal or less ideal. And so this equation works well for ideal gases. You know, so for example, if somebody were to say, okay, let's calculate the volume of the steam at minus 60 degrees Celsius. You're going, at minus 60 degrees Celsius is not going to be steam, it's going to be a block of ice. And so why would we be using this equation, which works for gases, to calculate the volume of a block of ice? And so this equation can be misused. What I mean by misused is this. There's nothing in the equation that tells you, hey, it's not valid, you know? It's not valid to use at that particular temperature because it's no longer a gas. And so people will go ahead and calculate it, but alarm doesn't go off. People will get a number and think their number is correct, but they have to look at what's going on. So all this derivation stuff, we're going to skip all that stuff, and we're just going to go straight to the ideal gas law. The ideal gas law is a composite of these three. You don't have to know that, but you should know the ideal gas law. PV equals nRT. PV equals nRT. P is the pressure, V is the volume, N is the number of moles. T is the absolute, you know, the Kelvin temperature, the absolute temperature. R is the gas constant. And, you know, the gas constant depends on the units. For example, do you want to use PSI for pressure, or what do you think the most common unit for pressure is? Atmospheres or bars? Yeah. Atmospheres or bars are, you know. And so the easiest thing to do is, since we are, let me just check something really quick. Since we are in the US, what's more common, atmospheres or bars? Atmospheres is more common. So we're going to use atmospheres as a unit for pressure. For volume, gallons or liters? Which one's more common? Liters. Liters. In science, liters. Gallons are more common with everything else. Number of moles is just number of moles. T is Kelvin temperature. So the gas constant, R, is we're going to memorize this to 4 sig figs. 4 sig figs. 0.08206 liters times atmosphere divided by mole times Kelvin. Liters atmosphere per mole Kelvin. Actually, you don't have to memorize it. I'll give it to you. So what we do is there are different applications. So for example, if we want to calculate the volume, what do we need to know about the gas? We need to know the pressure of the gas, the temperature, and the number of moles. Then we can calculate the volume of the gas. If we want to calculate the pressure, then yeah. So basically, pressure, volume, number of moles, and temperature are used to characterize a gas. And so if we want to solve for one of these, we need to know the other three. And so that's one application. And so in this case, let's say a 0.1000 mole sample of helium is placed in a piston and heated to 25.00 degrees C. The volume is adjusted to 4.600 liters, and the resulting pressure is measured at 0.5319 atmospheres. Use these data to determine the value of the universal gas constant. So this is experimental determination of R. So we know the pressure, the volume, the number of moles, and the temperature. So we can solve this equation for R, but R is already known, so this equation is just for verifying it experimentally. So rearrange the equation, solve for R. R is equal to PV over NT. And then calculate it. So they get 0.08206 liters atmosphere per mole Kelvin. This is good to 4 sig figs. So they got 4 sig figs here, 4 sig figs here, 4 sig figs, and then 5 sig figs here. This is called determination of a single variable. So if we want to solve for one of these, which is a single variable, then we need the other three. So that's, see, if all but one variable is unknown in the ideal gas equation, then you use algebra to find it. So let's see if we have an example of that. Here. All right, this is an example of a single variable. What is the pressure? So we're looking for the pressure. If we want the pressure, then we need the volume, the number of moles, and the temperature. We want the pressure in atmospheres, in the helium. So we have the volume, 0.77 liters. So throw that up here on the floor. The volume is 0.77 liters. We have the temperature, except the temperature is 22 degrees C. 22 degrees C is going to be what in Kelvin? 295 Kelvin plus 273. But we don't have the number of moles. The amount of gas in moles, we have the amount of gas in grams. And so we have 1.0 grams of helium. Well, we could just do gram to mole conversion. Then we can get the moles of helium. And so we'll need the molar mass of helium off the periodic table. The molar mass of helium is 4.00. 4.00. Since it's only one, it's not, you know, normally I go 2 decimal places. But actually, we're okay with 2 decimal places. This is only 2 sig figs here. The convention is we need at least 3 sig figs here. So we could go 4.00, which would be okay. To minimize round-off error, your conversion factor should have 1 more sig fig than what your given is. So we're given 2 sig figs here. I need to make sure I use at least 3 sig figs here. I could go 4, you know, but if I go 4, it's going to be 4.03. And so it comes out to a quarter mole, 0.250 moles of helium. So 2 sig figs, you know, will allow them to carry 1 extra. And then we just plug those into the equation here. What are they doing here? Your book loves to do this. Your book loves to come up with lots of variations of the equation. I don't. I like to just keep one equation and then just get everything in the right units. If I get everything in the right units, it works out. So the pressure is equal to P equals nRT. So it's nRT over V. Now I did the conversions here. We could have done the conversions in the equation itself, but since I like to keep the equation the same always, I do the conversions out here. 0.250 moles helium. Now, the ideal gas law doesn't care what the gas is. It could be helium, hydrogen, oxygen, steam. Doesn't care. Because it's just, these are all physical characteristics. We're not looking at the chemical properties of the gas. You know, the chemical properties of the helium are going to be quite a bit different than the chemical properties of oxygen. So. R is 0.08206 liters times atmosphere mole Kelvin. T is 295 Kelvin divided by V, 0.77 liters. So I just got to make sure the units cancel each other out. And that's how you know, correct? So the moles cancel out the moles, the Kelvin cancel out the Kelvin, the liters cancel out the liters, and I'm left with atmospheres. Well, that's what I want. I want the answer in atmosphere. So they get 7.9 atmospheres. I don't particularly like that they don't show the rounding step. In fact, I dislike it. And so I'm going to just calculate it. 2.25 times 0.08206. The other thing I don't like is they make you learn R to 3 sig figs. In Chem Chem 1A, you have to learn R to 4 sig figs. So you might as well just start learning it to 4 sig figs now, rather than 3 sig figs now and then 4 sig figs later. So 0.08206 times 295 divided by 0.77. And so I end up getting 7, I'm only allowed 2 sig figs, so 7.875 atmospheres of helium. Now we can round it to 7.9 atmospheres of helium. Wow. Wow. 7.9 atmospheres. That's a high pressure balloon. You know, that balloon's got to be really strong to withstand that kind of pressure. 7.9 atmospheres. Think of, think about when you're going swimming, like in a pool. If you go swimming in a pool and you go like 9 feet deep, that's just like a third of an atmosphere more. So let's say normal pressure is 1 atmosphere, you're at 1.3 atmospheres if you're 9 feet deep, I think. Is that right? Oh, something, yeah. You'd have to, you know how deep you'd have to go to get 2 atmospheres? You'd have to go 30, over 30 feet, like 33 feet deep underwater to get 2 atmospheres of pressure. 1 atmosphere from the air, and then 1 atmosphere from the water, the weight of the water. This is 8 atmospheres. It's pretty high pressure. All right, so this is, this type of problem here is pretty straightforward. This is algebra, and it's not, sometimes we'll have to do conversion. I mean, they made it a little bit more difficult because they give us grams instead of moles, so we had to do gram to mole conversion. And they'll make it more difficult by temperature. They didn't give us Kelvin, or volume. They won't give us liters, so we'll have to do some conversions. Now, your book loves different equations. They'll make a new equation. So oh, they didn't give us this, so I'm going to make this equation. Oh, they gave us grams instead of moles. Use this equation, right? And then your book also does this. They love to give you different R values. Oh, they gave us this unit instead of that unit, so they're going to give you a different R. And so, rather than memorizing a whole bunch of different equations and memorizing a whole bunch of different R values, just keep 1 R value, 1 equation, and then convert everything into those. It's easier than learning. Okay, if we're going to have to learn additional equations, then there are a number of equations that are going to be very useful. And these equations are variations to it. And one equation is for gas density. Gas density can be derived, the equation for gas density, so we can calculate, there are 2 ways to get the gas density. 1, we can calculate it. 2, we can measure it. Well, what would you rather do? Measure gas density or calculate it? Calculate it. You don't have to go in the lab and do all that stuff. And so gas density, D, is equal to mass over volume. So grams per milliliter, or for gases, we usually use grams per liter because gases are about 1,000 times less dense. And so if we use grams per milliliter, it's always 0.001. 0.001 is a hassle. And so why not just do 1 gram per liter instead of 0.001 grams per milliliter? And so gas densities are typically in the units grams per liter. So the volume will be in liters, the mass will be in grams. Now, we could measure it. We could just weigh the gas and then measure its volume, but that's a hassle. And so there's alternate ways of doing this. The alternate ways of doing this is this. We're going to solve the ideal gas law for V. And so if PV equals nRT, then what does V equal? PV equals nRT, then V is equal to nRT over P. And so then we're going to substitute that in here. And so we're going to get the mass divided by N then what we're going to do, that's for the volume. So what we're going to do next is we're going to invert and multiply. So it's just going to be the mass times the pressure divided by nRT. Now this is looking like an even bigger mess. This looks like an even bigger mess because now we have to measure the mass, which we had to do before. But now we'll have to measure the pressure, the number of moles, and the temperature. That's even more work than before, isn't it? It's even more. But there's something that you might not see here, and that is this. Mass is in what units? Grams. And then N is in what units? Moles. Grams per mole. What is grams per mole? Grams per mole is the molar mass. And so what we can do is mass over N, this is equal to the molar mass of the gas. And so what we're going to do is we're going to instead rewrite that as Mn, which means the molar mass, times P over RT. And so what this does is like helium. What's the molar mass of helium? 4.00 grams per mole. If we know the molar mass, then you can pick any pressure and any temperature and calculate the density. So what is the density of helium at, let's say, 8 atmospheres and 100 degrees C? Well, that's easy because pressure is 8 atmospheres, temperature 100 degrees C, we'll just convert it to Kelvin, 373 Kelvin, and then we can calculate it. What is the density of helium at half an atmosphere and minus 60 degrees C? That's easy too, we'll just calculate it. And so with this equation, we can calculate the density of any gas as long as we know the molar mass of that gas at any pressure and any temperature. And so this equation is very useful to know. So if you're going to do all these variation equations, well, this is a critical one, and it's just derived from the ideal gas law here, and the density of the gas conversion. So this is worth knowing here. So what is the density of helium at 22 degrees C and 744 torr? So why don't you try this calculation